In this video, what we're going to learn today is reduction of multiple subsystems. So the objective of this particular video lecture is to reduce a system with multiple subsystems into one single transfer function. So first of all, the question would be, what is a multiple subsystem? Right? What is multiple subsystems? So we know that, for example, we have seen before, we have constructed multiple transfer function of different systems. For example, let's say we know by now how to construct a transfer function of a system with, let's say, a rotational system with gears and load, right? And then a transfer function of rotational system, we can study with a certain input and certain output. So the input usually, for example, we put an input of theta, let's say I'm going to call it here theta S, theta input S, and then what we can have in output will be theta load. For example, imagine you have a shaft with gears and then and training or driving a load, you could have theta LS in the output, right? And we have also seen that a rotational gear system with gearings can be driven by a motor, right? So a motor, it is another transfer function with the output is now theta. So now we could as well call it as theta ms. So theta motor. Theta motor is the input to the rotational gear system with load, but theta m is an output to a transfer function of DC motor, right? And it has an input of, this time, it's not a mechanical input, it is it is an electrical input. So electrical input that we put into it was a voltage U motor S, right? So this is a sample of multiple subsystem where you have transfer function of different system connected to each other. For example, let's take a more relevant example. Let's take an example of an electrical car. So you have a gear train system that have a certain load, but theta ls now becomes an input to another subsystem, which is probably or could be the system of the drivetrain or the tire, right? So from theta L now it goes into the tire to produce another theta, which is, let's say I'm calling it theta T, which is theta tire. So this is the movement at the end of the tire. So in input, what you have is a voltage, and at the end you have, in the middle you have theta of the motor, and then you have theta load on the gears, and then at the end you have theta tires of your vehicle. But of course, in electrical cars, what we have, we don't put voltage into it. What we put is a certain command, a certain input of speed. Let's say it corresponds to basically an action of pressing the pedal. So action pressing the pedal, there is also a transfer function in it, right? There's a transfer function in it. Let's say I'm going to call the transfer function now as JS. So this is the transfer function for what we might call a controller. So you have a controller which is a pedal. So the input that you put into it correspond to a certain theta tire, but theta tire command or theta tire that you wish for. So you have basically in the far left side, you have an input which correspond to what we call it desired output, and the end you have the at the end here theta ts, you have the actual output. And in a system like this, usually you also have a feedback loop. So we have seen that there is open loop control and closed loop control. Usually what happens is you wish for some theta tire, but at the end you set it to friction or disturbance, for example, wind speed, or probably there is friction variation between the tires and the road. So theta T here could be different from theta tire that you wish for. So what we do usually is we have a feedback you measure theta t, the actual theta t, and you have another transfer function here. Let's say I'm going to call it as, we have j, k, ls. So this is a transfer function that correspond to the sensor. So it takes the measure of theta t, and then it translates it into a certain signal, and then the signal is then compared with our input, right? So to calculate the error, and then the error is injected back into the controller. So my drawing here is not properly done, but if you look into feedback system, this is how usually it is constructed. So basically in our system, what we like to do, if we want to study the system, let's say this is an electric car, EV. If you want to study the system of an electric car, so the speed control of this electric car, what we need to do is basically, if you want to study the system, it means that we have to study the transfer function. Because if you remember in a few first classes, what we did was we put, when we want to study the dynamic of the system, we put a certain input into the input of the system, let's say a step, right? And then we will study what happens in the output. How does it react? And then it's in the output that we measure and calculate the performance. So in order to do that, we have to study a transfer function. But now the problem is in here, you have multiple transfer function. So this is what we call a system of a system with of a multiple subsystem. It is a single system, a huge system with different subsystems. So what we need to do the objective of this class is to basically, from this complex system of multiple subsystems, we want to reduce it into one single transfer function. As I call it as G1S, where your input is the input of the original system. It's the same system, so it's theta command tire, and the output is theta tire in actual measure, right? So we want to convert the whole system, complex system, into only one single transfer function, because now it will be easier to do the study of the dynamic of the system, like we have done in first few classes, right? So the objective is to reduce it. So in order to reduce it, what we do is we have to know, identify the components of a block diagram, and then we have to know the type of arrangement of the block diagram, and we have to know how to reduce them, right? So very quickly we'll go through this. The first thing is components of block diagram. So when you have a block diagram like this, there is a few components that you have to know. All the things that are put in, that are noted in the arrows, they are signals. So there are signals. There are input signals to a system and output signal to the system. So an output signal to, for example here, an output signal to HS is an input signal to GS. Theta LS is an output signal to GS, but it's also the input signal to KS. So the thing that you've seen in lines, in arrows, they are signals. Okay, and the other components, what are the components? These symbols. I'll highlight it in yellow. These symbols, what is this symbol? This symbol is what we call a summing junction. So what is a summing junction? What summing junction does is it does operation on two signals or more, two or more signals. For example, here in this example, in this particular example, we had theta star tire, and then we have a summing junction with a sign plus and minus, and on the lower side we have theta, let's say theta TS. So what summing junction does is, in the signal at the output of the summing junction, what it does is it is equals to theta star minus theta t. That's what it does. That's what it does. Okay, I'll use another example with an easier parameters. Let's say you have x s here, you have y s here. The signal that comes out of the summing junction, it is xs minus ys. So it depends. It really depends on the symbol that you have in the summing junction. For example, here it shows plus on the left hand side and minus on the lower side. So it means it's xs plus xs minus ys. If both shows minus minus, then it is minus xs minus ys. If it's minus plus, then it's minus xs plus ys. So I think you got the idea. So that's what we call a summing junction. And then another thing is this point. So I'll highlight here. This point, this particular point, where you take the signal and then you measure it using a sensor. So that point, this is what we call a peak-off point. So what happened in peak-off points is basically the signal separated in two parts. Theta s goes to the output and it goes into the feedback as well without any change of the signal. It's not like a cut. It is a signal. It's not a current, as we remember, because student might think of it just like a current where it gets into a node, then it will separate into two current, theta 1 and theta 2. But no, in automatic control, in this kind of block diagram, when we have a pickup points, what happens is the signal it goes to both sides and it maintains its value of theta t. So that's what pickup points is. And then next thing, so that is components of block diagram, right? So the components of block diagram, I recall it back to you. There are signals, there are summing junctions, and finally peak-off points. Now we have to look at different types of arrangement of blocks, right? So arrangement of blocks. There is basically only three types of arrangements of blocks. The first one is what we call blocks arranged in cascade. Cascade means when the transfer function is put in what we call, if it is an electrical circuit, we would call it in series, right? Cascade is the same thing as in series. So if it has GS, HS, and JS in this composition, this is what we call an arrangement of cascade. For example, here in our system of electric vehicle, we have HS, GS, and KS. They are arranged in series. And then secondly, the second arrangement is what we call an arrangement in parallel. So you get the idea. Arrangement in parallel means when you have one signal and then separated into at the peak-off point, it is separated into multiple branch, and then it goes into different transfer function, for example, right? So this is what we call in parallel. And then the third one, that is what we call arrangement in feedback form. So you know what feedback form is. Feedback form is when you have one transfer function, and then you have another transfer function that get the feedback and then being compared with the initial input. So this is what we call a feedback transfer function. So now, once we know the components, the elements of block diagram and the type of arrangement, we're going to see how do we reduce this arrangement of blocks, cascade, parallel, and feedback. Okay, so we look one by one, starting from cascade. If we have a cascade, so we're gonna show the proof. We're gonna show how to reduce and the proof of the reduction. So in cascade, first one in cascade. So let's imagine you have an input of Rs, and then it goes into multiple transfer function. So I'm not gonna write the S for transfer function because it's gonna take a long time every time if I have to write between parentheses S. So what I want you to assume is every time I write a signal or transfer function, there is a S at the end of it, right? So RS, so I have here G1 S, and then I have G2, and then next transfer function G3, and then the output, let's say I call the output as CS, right? So how do we reduce this? In order to reduce this, it's simple. We know that at the end, what we want is you want it to become one single transfer function, GS, with the input, the same input. I want to maintain the same input because if they are equivalent, it means their input are the same, RS. And then the output, I want to maintain the same output, CS. So now the question is, what this GS equals to in terms of G1, G2, and G3? So in order to study that, we have to assign a name to every signal that we have in the complex form, in cascade form. Let's say I'm going to call this signal here as X1S and here as X2S. So we're going to go step by step by identifying what S1S is, what X2S is, and then finally identifying what CS is, and we'll see what happened. So here we know X1S, what is S1S equals to? It's RS multiplied by G1S, right? So that's pretty simple. X1S is also the input to G2, right? Let's see next what X2S equals to. X2S equals to, we know X2S is basically the input, X1S, multiplied by G2S. And we know that X1S, we've seen here, X1S is basically RS G1S. So it's RS G1S multiplied by G2S, right? So now we have X2. And then we go finally to CS. We'll see CS in terms of all these transfer functions that precede. What is it equal to? Okay, CS. So we know CS from the final transfer function, it is X2S multiplied by G3S. So it's X2S multiplied by G3S. And we know from here that X2S is actually RS, G1, and G2. So it's RS multiplied by G1 multiplied by G2, G2, and multiplied by, you see here, it's X2S multiplied by G3S. So we can see that we have CS, RS, and all the other transfer functions. If we were to write the transfer function GS here is in the simplified form. GS is CS. We know that GS is CS over RS. And if we apply into this equation over here, CS over RS is, what is CS over RS? CS over RS is basically G1S, G2S, G3S. So you see, if you have a cascading transfer function G1, G2, and G1, G2, and G3, it is basically equivalent to one single transfer function, and that transfer function equals to what? That transfer function equals to the value of G1 multiplied by G2 multiplied by G3. It is as simple as that. So this is also equals to, you have RS in input, and inside you have G1, G2, G3, CS. So it is the exact same thing. This can be simplified into this. So that is for cascade. I think it's pretty easy and straightforward. So now let's go and have a look at what if we have a parallel transfer function, right? So a parallel transfer function, we've seen before. Parallel transfer function is when you have an input, one single input, right? And then at a peak off point, it is separated into let's say I'm going to say it's separated into three parts, and then it's multiplied by three functions, G1, G2, and G3. And then they are joined back together by a summing junction. Let's say I'll say it is plus everywhere to give an input of CS. So again, how do we transform this into one single transfer function where you have the same input RS and the same input CS? What is GS equals to if the system is basically something in parallel? So in order to study that, as usual, we have to to assign to identify the signals and study the signals one by one. Right? Let's say I call this signal here the output of G1 as X1, this one as X2, and here as X3. And then what we need to do is to identify what X1, X2, X3 equals to, and then what's their relation with CS at the end. And then develop the transfer function of CS over RS. Okay, X1S, one by one. What is X1S equals to? X1S is RS multiplied by G1. X2S, what is it equal to? The same way, it's RS multiplied by G2S. And X3 is RS multiplied by G3S, right? And then at the end, we have CS. What CS equals to? CS, we know there is summing junction here. So CS is X1S plus X2S plus X3S. And we know the value of X1S, X2S over here. So it means they are equal to, what are they equal to? They are all equal to RS multiplied by the transfer function. So I can factorize RS. So it is multiplied by G1S plus G2S plus G3S. So by now, the transfer function GS here, this GS, we know that GS is CS over RS. And if we write CS over RS here, we can see that CS over RS is basically the sum of G1 plus G2 plus G3, right? So this is the transfer function, the simplified transfer function when you have only one block. So if I have to redraw the transfer function, the new transfer function simplified into one single block, you'd have the same input RS, but inside here you would have G1 plus G2 plus G3S, and then you have an output CS. So what's the difference with cascade? In cascade, the equivalent transfer function is the multiplication of those functions. In parallel, the equivalent transfer function in simplified is equal to the sum of the transfer function in parallel. And then the third one, we have the last one, which is the feedback transfer function. How do we simplify a feedback transfer function? So a feedback transfer function is a function where you have an input, let's recall, and then it is compared with an output. And in input, you have a transfer function. Let's say I call the transfer function as GS. So you have the output of CS, and you take the feedback measured into a sensor. Let's say the transfer function of the transducer or the tensor is called HS, and it is compared in this summing junction, right? To calculate the error. Okay, how do we simplify this into again, one single transfer function of the same RS. Let's say I want to call it GS, the simplified transfer function, and the output CS. How do we simplify it from this feedback transfer function to become one single transfer function? So just like all the things that we've done before, we will identify first the signals. You have to identify what the signals are. Let's say we will call this signal here as ES. So why do I call it is ES? E stands for error because it is the comparison between the input and the output, right? So it's why we call it ES. Here it's ES. Here we know that it's CS. The thing that get into here is also CS, it's the same CS. So the rest is this signal. This signals, I don't know what it is equal to, right? But the thing that I know is it is equal to the signal CS multiplied by HS. So here I can write the signal is basically CS multiplied by HS. So we have all the signals. Now we have to identify what they are equals to and try to write the function CS over RS to find basically GS, right? So let's write what ES equals to. ES equals to RS minus CSHS, right? You can see that, right? So ES, it is the output of the summing junction, and the summing junction, what we do is RS plus RS minus CSHS. Why is it here CSHS? Because in the input of HS, we have the output signal of CS. So ES equals to RS minus CS HS. Okay, next. So it means that CS can also be written in function of HS, right? Because there's a loop in here. So let's write what CS is. And then if we look at CS in a simpler form, we know CS is ES multiplied by GS. So what do we do next in here? What we want to do is we want to arrive at the end to write CS over RS. We have CS here, we have RS here, but the thing that we know what transfer function HS here, but the problem is that we have these signals ES that we don't know what the value is. So what we have to do is to replace this equation, this ES in this equation, into the first equation. So from this equation, we know that ES equals to CS over GS. And if we replace into the first equation, it becomes CS over GS equals to RS minus CS HS, right? So what do we do next? What do we do next? What do we do next is to basically to put RS on one side, the input, and to put CS on another side, which is the output. So if we put CS on one side, so we have CS here, we'll have to move it on the other side. We have CS over GS plus CS HS equals to RS. And if we factorize CS, we have CS multiplied by 1 over GS plus HS equals to RS, right? I'm going to come up here. So we can write CS over RS, right? CS over RS. CS over RS now becomes 1 over GS plus HS, right? So that's what the transfer function looks like. And if you do the math, this is in a simpler form. This would equals to GS over 1 plus GS HS. So this is GS in one single transfer function form. So if I have to change this feedback transfer function into one single transfer function, the transfer function is RS, and inside here it's GS over 1 plus GS HS. And you have the output of CS. So that's the equivalent transfer function of a feedback arrangement or feedback form. You have GS, which is this transfer function on the top, or what we call a forward transfer function. GS over 1 plus GS multiplied by HS. HS is what we call a feedback transfer function. This is what we call forward transfer function. This is what we call feedback transfer function, right? So it's forward transfer function over 1 plus forward multiplied by feedback transfer function. So now you have the simplification of three arrangement of transfer function. I'm sorry, let me see how can I do this. Okay. So we have the transfer function simplification of in three form. If you have a cascade G1, G2, G3, the equivalent transfer function is the multiplication of G1, G2, G3. If you have a parallel transfer function of G1, G2, G3, is equal to the sum G1 plus G2 plus G3. And if you have a transfer function in feedback of GS and HS, is equal to GS forward transfer function divided by 1 plus the product of forward and feedback transfer function. Okay, so that's how we do the simplification of different arrangement, the three arrangement. Next thing what we need to do is what we can do is what we call a block rearrangement. A block rearrangement. It is sometimes necessary to change the position of a certain block to make it easier to simplify the system. All right. We will have a look at it in a second video, because now the video has gone to half an hour range, so I don't want it to make it longer. We'll do a second video in relation of multiple subsystem, and I see you in the next video. Thank you.